necessarily have some uncertainty associated with it. And he realized that you could do some sort of novel form of coding. Actually, his original idea was to make quantum money. And the idea would be that the bank would send you basically a bunch of qubits. It would send you, it's fine, it would send you qubits that were in particular states. And let's just say it would send qubits either 0, 1, or 0 plus or minus 1 states. And it would know what it sent off to you. And at the end, when you returned the money to the bank, if it was the same money, then the bank would know, because it knows what it originally encoded, would know how to measure each of the slots. And if it knows the right basis for each of the slots, then it should measure the same state that it originally put into the thing. Yeah, so we'll see this is very similar to how quantum cryptography is going to work. Now, the problem with this, it is unhackable, it's unforgeable, so that's not a problem, that's a good thing. The problem is you need a quantum memory that lasts as long as you're carrying your money around. That's a kind of a problem when our best quantum memories are like a millisecond now, and a lot of them are closer to microseconds or something, so that's not really so useful as an application. But nevertheless, it did sort of sow the seeds, as it were. And my understanding is that Stephen Wiesner met Charlie Bennett at a conference or something like that, and told him about the idea. And Charlie Bennett was really the person who then said, "Oh, this is actually really quite significant. We should publish this." And that started the entire. That started the whole thing. So this is the first. This finally got published in 1992, but again, it was derived a long time ago. So the idea here is to try to use quantum states to be able to do better classical information processing. So to be able to have more classical information transmitted down a pipeline. And so the scheme of this super dense coding is that, okay, so in this case, sure, I'm going to get these backwards, but now we're having Bob just kind of get information to Alice. So there are 2 classical bits of information he wants to get to Alice, but he doesn't want to have to send that much information. So the way the protocol works is that Alice and Bob will each get 1/2 of an entangled pair, and then Bob will do 1 of 4 unitary transformations to his half of that. So if Alice and Bob are originally, I'm going to need these a lot, so let me just write them down. Writing these in a polarization encoding, but it could be any kind of encoding. Just treat these as generic 0s and 1s, if you will. So so by doing just a unitary transformation to one of the photons, like the first photon, I can convert any Bell state into any of the other 4 Bell states. So, for example, if I do an exchange of horizontal and vertical, then that will. On one of the 2 photons, let's say the second one, it'd be easy to see, then HH plus VV would become HV plus VH. If I instead put a minus sign between the horizontal and vertical, then I can go between these 2 of the phi plus states. And if I do both of those things, then I can get the psi minus. Okay, so then I send, Bob then can send his single photon back to Alice, and Alice now has both of the photons, and so in principle then she can measure what is the Bell state of those 2 photons. It'll be in one of the 4 states, and therefore with 4 messages that's equivalent to 2 bits of information. So in this case, Bob has been able to transfer 2 bits of information, but he's only sent 1 photon to Alice. So we would say that the capacity of the channel in that case in bits is log base 2 of the total number of messages, so there would be 2 bits per photon from Bob. Yes?
Don't you only store what you did to photon number 2, so aren't you only sending 1? piece of information? Why does it need two?
Because when Alice, Bob is only doing, one of four, he's doing one of four transformations. And when Alice has the two particles, in principle, she can measure which of the four Bell states there are. So by sending one photon from Alice to Bob, from Bob to Alice, he's been able to imprint on her or send to her which of these four transformations he did. So that's 2 bits of information.
Oh.
Yeah? Other questions? Okay. Okay, so this is just a maybe a nicer picture of that, and now we're actually going from Alice to Bob. Now, one of the things is that we do need to be able to make this Bell state measurement, and we will see that that is not as easy as it sounds, not as easy as we would like it to be, unfortunately. Okay, so nevertheless, right, so I can, all of the transformations that Bob is doing, if I think about the Poincare sphere, I can get those same transformations either by doing nothing or by doing rotations about any one of the axes, about the vertical axis, about this horizontal axis, or about this axis, or about this axis. I can convert any of the Bell states to any of the other Bell states. Okay. So this is using a slightly more conventional notation now in terms of gates between the bits. So let's see, a couple things to note. So first of all, this is what we would like to have happen. Now, unfortunately, I can't really get my photons to interact strongly with each other, with current materials. So typically one photon interacts with another photon at the level of 10 to the minus 9 or 10 to the minus 10 or 10 to the minus 6 or something like that. So what that means is I can't actually do a normal, a gate, basically. A gate would enable me to measure exactly what Bell state I had. So I can do probabilistic schemes, and that's in fact what you calculated on your homework. So in your homework, you calculated this case of sending in 2 photons onto a beam splitter, and depending on which of the 4 Bell states they're in, you will either get 1 photon going to each output port. That happens for one of the 4 Bell states, as we'll talk about it again in a second. Or the other possibility is that you get, say, both photons going this way, or both photons going this way, and then, depending on what the polarizations are, for example, if you measure the polarization here, it might be that these are both the same polarization, in which case, again, they'll both go to the same detector, or it might be that they're opposite polarizations, depending on which of these 2 types of states. So the bottom line is that we can distinguish of the 4 Bell states 2 out of the 4, and the other 2, 2 out of the 4, and then the other 2 give the same signature. There are some other schemes that work that can distinguish all 4 of the Bell states, but then they're at most 50% efficient. So effectively, it's the same thing. So in fact, you can show that if you have linear optics and classical communication, the best you can ever do is to discriminate two of the 4 messages, two of the 4 Bell states, and the other 2 give the same signature. Therefore, in terms of sending messages, you can have 3 independent messages at best. So with 3 independent messages, then the capacity of that channel would be log base 2 of 3, or about 1.58 bits, which is still better than 1 bit. So we can ask a little bit how to understand this interference of the beam splitter. And you guys have already done the calculation in your homework where you just brute force it and you figure out what the answer is. But let's look at a different way of thinking about it. So the photons are bosons. So that means the total wave functions of the photons has to be symmetric or antisymmetric. It's got to be symmetric. If I look at what these various states are, psi minus is the singlet state, so psi minus HV minus VH. That is an anti-symmetric state. So in the psi minus case, the spatial wave function must be also anti-symmetric. Otherwise, you wouldn't get a total wave function that was symmetric. And for all the other three, the wave function, which are symmetric states, the wave functions have to be, the spatial wave functions also have to be symmetric, so that the total wave function is symmetric. So if I look at the four states, then the one in which the photons are, let's see, another way of looking at it. I know that if I were to just send in HH, I would just get a normal Hongo-Mandel dip, and both photons would go the same way. And if I were to just send in VV, same thing, the photons are the same, the photons would go the same way. Okay, sending in HH plus VV, I get the same behavior. Sending in HH minus VV, I get the same behavior. If I look at HV plus VH, it's like, okay, well now it looks like they're different, but if you write HV plus VH in the diagonal basis, that ends up looking like DD minus AA. Okay, so in the diagonal basis, these do have the same polarization, and they again end up going off the same way. The singlet state is the one that in any basis at all, and every possible basis, these two states are always orthogonal, right? So in this case, I will have the case that the two photons go off in opposite directions at the beam splitter. Okay. So that's just all the thing I just said. And I guess I did want to just add one more thing here, which is right there. I guess I'll do it here. So this could be polarization, or obviously it could be spins instead, or it could be photons in two different time bins, or it could be atoms in ground and excited state. So any of these degrees of freedom will have the same sort of behavior if I'm looking at this kind of a system. Okay, so this was in fact this was the very first experiment to actually try and demonstrate this with, again, a source of polarization in tangled photons, initially in the state, let's say HV plus VH. And then we have, and then with wave plates we can control basically which of the states we have. And then we'll just look behind these polarizing beam splitters, which are themselves behind this regular beam splitter, and just see what we see. And as we expect, for example, if I'm looking at coincidences between detectors in the top half and detectors in the bottom half, if I have the state psi plus, that's this one, so I don't expect to see any coincidences, assuming the path lengths are balanced, so that's why that goes to 0. And similarly for psi minus, that's the singlet case where the photons always go off in opposite directions. So that's looking pretty good. So there's a total of, again, 3 different types of states that we can distinguish. So in principle, you can have a capacity of 1.58. And when you actually calculate what the capacity is, because of errors in the system, the actual capacity is only about 1.2 bits per photon. So, okay, it's demonstrated that you've done better, but not really as better as you would have liked to have done. And again, partly the issue is that we can't distinguish all 4 Bell states, and part of the issue is just that even the 3 that we could distinguish, we're not distinguishing all that well in that first experiment. So there was this other paper that claimed to do claim teleportation, but for the moment, let's not worry about teleportation, and we'll just worry about, can I distinguish all the 4 Bell states? And in this paper, the claim is, yes, all 4 Bell states can be distinguished. Okay, so that's a pretty big claim. And the way that it works is that we'll take the 2 photons that are being presented to us, and we will try to add them together to do some frequency generation. So I'm going to try and take these 2, let's say, red photons and combine them into 1 blue photon. And in the first crystal, it's only going to work, for example, if they have the same polarization. And if they have the same polarization, then they'll be upconverted to blue, and then I will take that out and I'll try to see that blue photon and I'll ask what the state was. And I'm going to do this in 2 different crystals, so that if I had HH plus VV, for example, the HH will convert in this crystal and the VV will convert in this crystal. So then the upconverted photons, the blue ones, if it was HH plus VV, would become H plus V, so it would be diagonal, and it would show up here. And if instead it was HH minus VV, when that converted, it would become H minus V, which is anti-diagonal, and then it would show up over here. So I can detect those 2 states. If instead the 2 photons coming in had perpendicular polarization, they just don't do anything in this first crystal. They completely pass through it because it only couples photons that have the same polarization. They completely pass through it. This only reflects out the blue photons. And then in the next crystal, now if they have orthogonal polarizations, now they can get upconverted. And it's the same thing. If it's HV, they'll convert in this one, and if it's VH, they'll convert in this one. And if it's HV plus VH, then you'll get, they convert, and then, let's see, I guess, in this one, the HV gives rise to, say, a horizontally polarized blue photon, a high energy photon. And in this one, the HV gives rise to a vertically polarized pump photon. And again, if there's a relative phase between them, then that will show up in either H plus V or H minus V. So again, you'll see, depending on which detector goes click at the end. So you can detect all 4 of the Bell states, depending on which detector goes click. So that is very good. And this is just some of their data, which is showing this. There's a thing that's sort of hidden inside of their paper, though, which is that the only way that they could get this to work is if their input pulse had about not 1 photon in it that they're trying to work with, but if instead they had to repeat this with a pulse that had 10 to the 9 photons in it. So it can distinguish all 4 Bell states, but it only works 1 out of 10 to the 9 times. Not really very useful. You'd be better off doing the thing that only can distinguish 3 of the 4 Bell states, or whatever, 2 of them for 3 messages, but at least in principle works every time, whereas this only works 1 out of 10 to the 9 times. But if you could get your conversion to work more efficiently, so if you could get a very high nonlinearity so that when you put 2 photons together in the crystal, they actually did 100% of the time do that conversion, then this in fact would be the scheme that would just completely solve the problem. So this is just a plot of the channel capacity in some different experiments that were done. And classically, if you're trying to do this and you're just sending 1 photon along, you have a channel capacity of 1 bit. And we saw that what we would like ideally to get is 2 bits with super dense coding, but with linear optics, we can only get 3 messages, so that's at 1.58 bits. And then there's just a number of experiments that were done, both with photons and also with ions. It turns out that if you can incorporate more degrees of freedom, so if instead of just using Bell states like this, you can also incorporate other degrees of freedom, like the time bin, or like the spatial mode, or something like that. Then you can distinguish more of the Bell states that you have, more of the entangled states. So that's good. You can then get more communication per photon. On the other hand, you are also sending in. because you have more degrees of freedom, for a fair comparison, you have to use the fact that, well, classically, if I have more degrees of freedom, even if I'm not doing anything quantum mechanically, classically, I could send more information if I use more degrees of freedom. Right? So maybe just to ask a question to see if that makes sense. So let's say that I'm going to allow myself two time bins and my two polarizations. The question is, classically, how much information could I send with that? One photon, but I have, again, two polarization states and two time bin states. Two bits of information. You get one bit from this and one bit from this. No matter how you certainly don't have to measure this way. You could measure in other weird combinations of these, but you're always going to be limited by the dimensionality of the space. Let's just talk for a second about time. So let's say I'm using time bins. Question is, how many bits of information using time bins, not necessarily just two, if I don't restrict to that, how many bits per photon can I get? It's a big hoop to go through, but it's kind of oddly tilted, so it's hard to maybe hard to see what I'm getting at.
Doesn't it depend on the interval that you like measuring?
It does in a way. Do you want to say more about that?
So I mean, could potentially be like infinite, right?
Yeah. So if let's say I send one photon per day, and let's say that I can know. Let's not even do that, because I don't know the answer for a day. Let's say I can send one photon per year. Any idea how many seconds are in a year? This is so useful. The number of seconds in a year is equal to pi times 10 to the 7 seconds. So like the third decimal place or something like that. Useful number to carry around in the back pocket. So if I could resolve things to within 1 second where my photon was coming in, then the number of messages I would get would be log root 2 of pi times 10 to the 7. Okay, I don't happen to know what that is, but it's a big number, but it's not very, the logarithm really cuts down on that. And I've had to tie up my whole channel for a year, right? Because I only got one photon coming through. So admittedly, if I do this, whatever, I'll get, I guess it shouldn't be that much, right? So this is like 10 is like 2 cubed. Right, so this is like 21 bits, and this is like another couple bits. So this is something like, I don't know, 24 bits of information or 25 bits of information. So it's a lot of bits of information per photon, but I only got one per year, so it's only 24 bits per year. Not a very useful way to do things. Yeah. So in fact, this is, I believe this is the world record for this sort of experiment where they used, again, 2 degrees of freedom. They used both the timing degree of freedom and also the polarization degree of freedom. And with that, they're able to, if you do that, then you can distinguish all four of the Bell states. In fact, in principle, you can distinguish whatever 2 to the 2.81 is. I can't you guys have a calculator? Someone can quickly tell me. I think that's like 7 maybe. So I think so if you've got two polarization qubits, that corresponds to a 4-dimensional space. So that corresponds to the 4 states that you could in principle send. If you add on now 2 time bin qubits on each of the 2 things, that becomes a 16-dimensional space. So now there's a total of 16 messages in principle that you could send, but you can't distinguish all 16. You can only distinguish, again, whatever 2 to the 2.81 is, which I think it's 7, is that right? Yeah. So you can only distinguish 7 of the 16 states. Now 7 out of 16 is less than 2 out of 4. Just say that again. 7 out of 16. Removed all my chalk. 7 out of 16 is less than 2 out of 4. So fractionally, by going to these larger dimensional systems, although the overall number of messages has gone up, the fraction of messages has gone down. So, and the trend continues. So as you go to bigger and bigger systems, you detect more states, but a smaller fraction of the overall states. So this is not a win. In the end, it's not really a win. You end up doing more poorly. Okay, in any event, they were able to get a capacity of 1.67, which again is the highest that's been reported. That was a few years ago. So, question. Let's say we could do perfect superdense coding. So let's say we could really do the Bell state analysis, because I'm going to transfer the photons into atoms, and then the atoms can completely do this full Bell state analysis, or spins, or some other thing that doesn't have this limitation. So let's say that I can really distinguish all 4 of the Bell states. The question is, should we do superdense coding? Is this a thing that you should say, I'm going to invest in my quantum network so we can do superdense coding? This is a good topic for discussion. Talk amongst yourselves.
What kind of resources? Maybe if there's an error, it might be I have no idea.
There's an error
In the code.
I think it might be more set up like experimental.
Well, maybe it's expensive to see if if it takes up material resources, maybe it's just unless the material and maybe you're right, because it's hard to compare. I don't know if it actually is though. It's just
So let me sharpen up the question a little bit and say, let's say we're trying to communicate to Mars, or from Mars. And the question is, should we do this using superdense coding?
If so, then no. Yeah, you can't take 5 or Mars. That'd be kind of cool to do it fine.
Then we just set to page 2.1. I guess but for Mars.
Well, in this case, it's saying we can do it, should use it to go to communicate with Mars.
Yeah, I'm just trying to say that that's
More implementation of the error effect. There's a lot of inherent players in ours. So checking for errors.
then you need to
I don't know how
two to three
we did
people
it.
during the
You got the slide.
How long is the light taking?
You can't read multiple notes. You're saying you can't read multiple notes. Oh, okay. If you can.
But then you need to set it for 20 minutes, 40, to get the return
Too
trip.
many photos. The issue with this one is
I think we're assuming that whatever it is, 2/3 of the 9 or 10 cent, but
Okay, what do we think?
And you could have done 20.
Should I do,
It's more of a guess, but I wanted to know is it a matter of correcting for errors? Is it harder to correct errors in dance coding? I don't actually know.
I think it would be, let's say it's more or less the same, I guess, because there's some sort of rotation and you have to correct for some kind of rotation, so I think it's, of order the same difficulty. So who thinks yes, we should do it? Who thinks no, we shouldn't do it? Ooh, a lot of no's. Why no?
We kind of came to the conclusion that it depends a bit on how lossy your communication channel is.
Which is always somewhat lossy.
Yeah, because essentially each photon you lose, you're losing more information per photon. So there's going to be some break-even point, presumably, with the loss where it makes sense.
Right, so your explanation is that because you're carrying more information per photon, there could be a break-even point. The situation is really, in some ways, that's true, but I guess the point is we just look at it, that break-even point never exists in any real system. So, for example, if you're coming from Mars, where the losses are very, very high, where only 1 in 1,000 photons is getting through, very little of your message is actually ever getting through. In order to do this experiment, though, I have to send my quantum signals 1 photon at a time. I have to send it, and it has to be distinguishable from the next one coming in. So that means I can't send them any closer than whatever the detector resolution time is, 100 picoseconds, 10 picoseconds. Let's go into the future 5 years, 1 picosecond. Let's go into the future 50 years and make it a 1 femtosecond resolution time. I still can't send more than if I had 1 femtosecond resolution on my detectors, I can't send my photons any closer than 1 femtosecond with respect to each other. So at most I can send 10 to the 15. So the highest number of signals I would get if my loss is 10 to the minus 10, let's just say, to make it easy, would be 10 to the 5. I'd get 10 to the 5 per second things coming through of the 10 to the 15. So in other words, my actual success rate is really low. It's only 10 to the minus 10. That's bad. On the other hand, if you do things classically, I can send a pulse, my laser pointer, which is sitting somewhere else, my laser pointer maybe has 10 to the 16 photons in it. Or even, let's just say, 10 to the 11. 10 to the 11 would be more than, anyway, the laser pointer probably does actually have 10 to the 15 or something like that. 10 to the 15 photons, I can take a 10 to the minus 10 hit, and I still have 10 to the 5 photons left. Or even if I started out with only 10 to the 11, I can take a 10 to the minus 10 hit, and I still have 10 photons left. I can still detect it. So the point is, the classical signal with all of its photons, it's much more tolerant to loss. It's not better per photon, but per photon is usually not the actual criteria that you want. So for quantum communication purposes, superdense coding, interesting from a theoretical point, but from a practical point is just absolutely not. And the only reason I'm stressing this is I have been in multiple meetings with people who are quite gung-ho, not quantum physicists, but people who see quantum and they know, okay, we're going to be able to use quantum to send much more information down the internet because we can use this super dense coding and you're going to be able to get all of Game of Thrones in 1 photon or something like that. Okay, it's not going to work out that way. Questions or comments? Okay, we're actually going to, I'm reordering things just a little bit so it'll help us make up a little bit of time. And we're going to jump to quantum cryptography. Instead of, we were going to do teleportation, but I'm going to start with cryptography instead. can read this fun old Dilbert cartoon. So it's always nice when your field makes it into popular cartoons and people start to know about it. I think the reason I like this quite a lot actually is that, you know, it mentions Bell's theorem, and I like the little asterisk, really no kidding. That's funny. A little bit of a wrong statement where it says that if you change the spin of one electron, the spin of the other electron changes too. Right? That's not, just to be, hopefully we now understand, that's not the case, right? If I make a measurement here, that changes what the measurement result is. It's not the case that if I exert a torque here, that exerts a torque here. That would allow us to send signals instantaneously. So we don't quite have that. Okay, so to understand quantum cryptography, it'd be good to first understand classical cryptography a little bit. And there are two ways we can break all of classical cryptography into two main settings. One of them is so-called public key encryption. And in public key encryption, I'm going to have some number that I will transmit to the rest of the world, to everyone. And that number, it turns out, in one way of doing this, is the product of two large prime numbers. And I'm the person who knows what those prime numbers are. So I start out with the prime numbers, and then I multiply the two together, and then I send it to the rest of the world. And you can then use that to encrypt a message and send it back to me, and no one, except someone who knows what the product of the two prime numbers is, can decrypt the message. Even you, even though you knew what the message was, you can't decrypt the message. So you might normally think that, well, if I knew the original message, and I know the ciphertext, then somehow I know what transformation is happening, so then I could decrypt other messages. But it's not that way. Unless you know the product of the two primes, you can't solve that. So that's public key encryption. When you are like on a website that has an HTTPS, the S is probably not effectively that sort of protocol that's happening. The problem with that is that it's not provably secure, so it's not known whether or not factoring numbers into their prime constituents is a hard problem. It is believed to be a hard problem, mathematically, until 1984. And in 1984, Peter Shor says, if you have a quantum computer, in fact, you can factor numbers really quite easily. So quantum computers that was the first kind of main application, and that really launched the entire field of quantum computing, because we're quite interested in whether or not people will be able to crack every single code that we have. That would be a quite dangerous situation. Okay, the other method of encryption is instead of public key encryption, secret key encryption. So in that case, there is that's a two-party protocol in its simplest case. And the two parties, who are typically called Alice and Bob. So Alice has some message that she's trying to send to Bob. Maybe the message is, what are we having for dinner tonight? Not sure why that needs to be secure, but that's all right. And she'll put that into binary, whatever the binary encoding of this message is. The next step is that Alice and Bob are both assumed to have a key. A key is a random string of numbers, just a string of zeros and ones. They could, for example, get that key by using a quantum random number generator, which we know all about now. So I'm just going to pretend that this is my key. And then Alice will simply add the key to the bit string, the message to the key, bit by bit, modulo 2. So 0 and 1 is 1, but 1 and 1 is 2, but then modulo 2, that would be 0. So basically, she's taking the parity of the two. So if they're the same, I write a 0, and if they're different, I write a 1. And then this ciphertext gets transmitted over some public channel, phone line, Facebook page, whatever. And Bob also has the same key. 0, 1, 1, 1, 1, 1, 0, 0, 1. And then he just does exactly the same procedure, and if he does that, then he'll get exactly the same message that was sent. Okay, so this is known, it's a secret key encryption. Also known as a one-time pad encryption. That's because they used to use this in, I think it was World War II. I think this came in World War II. And the soldiers would go out on the field and they would have a pad, and on the top, let me explain where this name came from in a second. This is a secure method of encryption. In fact, as far as I know, it is the only provably secure method of encryption of anything, but it requires two assumptions. One assumption is that you're not allowed to reuse the key. So if you ever reuse the key for another message, that makes you insecure. And the way to easily see that that's true, sometimes like in the Sunday paper, they might have a cryptogram where they have a letter that's a message where they replace every letter in the message by a number. So like the letter S is represented by the number 7, and the letter A is represented by the number 2, or something like that. The reason that you can decrypt that is that every time the letter S appears, it's always the number 7, and every time the letter A appears, it's always the number 2. You know that S is, for example, the most most common, I don't know if it's the most popular, but anyway, it's the most common letter of the alphabet. So you look and you see which number appears most often. That's probably going to be an S, for example. So you can solve that because it's always, you're using the same transcription for every letter. If every time the letter S appeared, it was represented by a different number, then there'd be no hope of being able to crack that. So we can't reuse the key. And the second thing is that no one else is allowed to know the key, because if anyone else knew the key or part of the key, then they could do exactly the same thing that Bob does, and then they could recover at least part of the message. So the reason this is called a one-time pad is in the war, the soldiers had the pad, the top sheet of which was their key for the day. And they use that key, and then they tear off that piece of paper, and then they never use it again. So it's a one-time use in this case. Now, an anecdotal story, which is that apparently the Germans did this, and the soldiers discovered that those sheets that they tore off were like kind of right, like the right size for toilet paper. And apparently, when we went and we entered into some of their camps, some unlucky private in the army had to go through their latrines, but they did in fact recover a lot of material, and they were able to decrypt many messages because the pieces of paper were left behind, not really in a state that you'd like to read them, but when you're a private in the army, you don't really have a choice, I guess. So the question then is, well, how do you get the key from Alice to Bob? That really becomes the trick. So we could try to carry that key. For example, I could have a courier that has a suitcase that carries it from Alice to Bob, or I could have a phone line that I hope is secure, or maybe some fiber optic, like an electrical cable or a fiber optic cable. And the difficulty with all of those is the information is always being carried classically. And in a classical system, I can measure it without introducing any change on the state. So I can put my briefcase through a terahertz scanner and in principle read what's inside the briefcase, read what's on the paper inside the briefcase. If I have an electrical pulse going down a wire, if I just put a little induction coil there, when the pulse goes by, I'm going to have a little blip because the magnetic field will change. If I have an optical signal, a pulse going down a fiber optic cable, if that signal has, let's say it's a coherent state, because that's what we use, let's say it has an average of 10,000 photons in it, that's 10,000 plus or minus 100 because of the variance. So if an eavesdropper removes 10 of those photons, you have absolutely no way. It's physically impossible to tell that that's happened. So an eavesdropper, in principle, can measure every single pulse going down the wire, and there's no way to tell that there's any missing. Okay, so quantum cryptography, of course, gets around this by instead trying to use single photons in order to encode the message, encoding it in some degree of freedom of the photons. Okay, so here's our Alice. See, she's got this little key. I lost my let's see. Yes, Alice has her little key. And, okay, this is just the same protocol that we've talked about. Okay, so this is one way of doing this, the so-called Bennett-Brassard 1984 protocol. What? So for this, we'll start talking about using polarization to do the encoding. So we'll use either the horizontal vertical basis, where horizontal is a 0, vertical is a 1, or the diagonal basis, where diagonal is a 0 and anti-diagonal is a 1. And Alice is then going to send a whole string of photons, preferably exactly single photons to Bob, with one of the 4 polarizations, horizontal, vertical, diagonal, or anti-diagonal. And then for every photon that comes in, Bob is going to randomly decide to measure either in the horizontal vertical basis or the diagonal basis. And then he'll write down the numbers. Now, of course, if he uses the same basis that Alice is transmitting in, he will get the same polarization, because she's sending H and he's measuring the H3 basis. He'll get H, assuming there's no errors in the way. So Alice and Bob will then have a public discussion. They'll talk to each other on the phone, and they will exchange the information for every given photon that was detected by Bob. They'll exchange the information of what basis was used. So not the actual result, but what basis was used. And in cases where they use different bases, they discard the results because there's not necessarily any correlations at all in that case. But if they use the same basis, they keep those results. So this is the so-called sifting stage. And then the final data that they have should completely match. And that then comprises their secret key. Okay, so a couple things about that. One is that, it didn't say this in the description, but if Bob happens not to detect some of the photons, because they know when they're supposed to come in, it has to be a clocked signal, they know when they're supposed to come in, they can identify that he missed number 13, he missed number 14, he can identify which ones were missing. That's going to be critical. If they lose the synchronization, then you can't do anything. So that's okay. It doesn't hurt if you lose the photons. If you lose all the photons, that's not good. So an eavesdropper who cuts the channel, denial of service is pretty easy for quantum cryptography systems. But in any event, having fewer photons go through doesn't necessarily hurt the security. Come back to that in a little bit. Okay, so this is just a non-animated version of the same thing. And as I say, this was originally based on this paper by Stephen Wiesner using this conjugate coding for trying to make quantum money, basically. And it says 1983, which preceded the BB84 protocol. But again, it was really from quite a bit earlier, things that he had been studying much earlier. So the way that might look in practice is we might have for the moment, let's pretend these are single photon sources. Now, I'll come back to that in a second, where one of them is making horizontally polarized photons, one's making vertical, one's making diagonal, one's making anti-diagonal. And then I send them out. Okay, if they're true single photon sources, I don't need to have an attenuator. In reality, what people are often using is coherent states, so attenuated laser pulses in this case. And then I do have to attenuate them to the single photon level, send them through some quantum channel, and then Bob on the other side can measure what the polarization is, and by using, for example, this Pockels cell that allows you to rotate the polarization, say, by 45 degrees, so that you either are measuring in the horizontal vertical basis or in the diagonal basis. And in this case, when they do their sifting, Bob is only going to use the right basis, or they'll only use the same basis half the time. But for that half the time, that 50%, the keys have a perfect correlation. Now, if there's an eavesdropper in place, as you guys saw in your homework that you already calculated, if they're looking at every photon, they'll introduce a 25% error rate. And again, the easiest way to see that is that if they're in the horizontal vertical basis and the eavesdropper is in the diagonal, sorry, if the eavesdropper is also in the horizontal vertical basis, she doesn't introduce any errors, but she's got to randomly choose what basis to measure. And so if she happens to measure in the diagonal basis half the time, then what she ends up sending on to Bob in this case is either diagonal or anti-diagonal. It doesn't really matter which one. Bob is measuring with horizontal and vertical. Both the diagonal and the anti-diagonal are equally likely to show up through either of these detectors, horizontal or vertical, but one of them is an error and the other one's not an error. So that you get a 50% from that, and also 50% that the eavesdropper chose the wrong basis. So up to 25% errors. The other thing that you saw in your homework is that if instead Alice and Bob are using all 6 states, 3 bases, so they're adding in, say, left and right circular, then the eavesdropper induces more errors, because in the third basis it's a 50% error instead of these 25%. So the net induced error rate goes up to 33%. That's good. Having the eavesdropper induce more errors is good, because it means it's easier to detect the eavesdropper. Or another way to put it is that if you have noise in your system, you can tolerate more error in your system and still be able to have a system that could be secure. The other thing I'll say is that in general, modern systems often do not use this randomly choosing between 2 bases. They'll do something which is asymmetric. So there'll be one basis, let's say that's fine, we'll just stick with it. We'll do one basis, say the horizontal vertical basis. We're mostly going to use that, let's say 90% of the time, for sending the key, and then only occasionally we check in the superposition basis as a control to see whether or not there's an eavesdropper. Now, if there's an eavesdropper, obviously you're only checking 10% of the time, so you need to accumulate enough data so that you can have confidence, and you have to be, what will I say, the 10% of time when you're checking for an eavesdropper, that has to be done at random, right? So it's not like Alice and Bob say, okay, now we're going to check for an eavesdropper, we're going to use the diagonal basis, because you have to assume that the eavesdropper hears all of those conversations, so it has to be done at random. But if you have a large enough data set, if there's an eavesdropper who's measuring, again, 10% of the data in this check basis, they'll introduce a large enough error to be detected. Okay, so what about an eavesdropper? Yeah, let's just talk about this. So why is this helpful? Why is this whole protocol helpful against an eavesdropper? There's a number of different ways or reasons.
You know if there is an eavesdropper?
You know that there is. How do you know that there is?
Based on the end, you can check the error rate that you got, and then.
Okay, so an eavesdropper, if there is one, will introduce errors. So that's one thing. So we can check some subset of the data to see if there are errors, and that will give us some information about whether there could be an eavesdropper. We'll always be conservative and assume that any errors that we get are due to an eavesdropper. So another reason why this is more secure than the classical case is that you can't an eavesdropper can't tap the line, because there's only one photon that's going from Alice to Bob. You would like it to only be one photon going from Alice to Bob. If an eavesdropper removes that photon, the eavesdropper does hold that photon now, so she can measure that photon, she can get whatever information she wants, but that photon didn't make it to Bob, so it just never becomes part of the key. So that's not going to work. The eavesdropper can indeed, well, actually cannot, I should say, cannot copy, cannot clone the photon. We did the no cloning proof, right? Did I ever show it here? Good time to do no cloning, because it's such an easy proof. I love easy proofs. Okay. Okay. So here's the bit I'm starting with. Here's the copy bit, but I'm trying to make a copy of. So if everything's working, if my copier is working, what will the state be? These are all going to be like super easy questions, so don't overthink it.
0, 0.
Very good. Okay, and if I send in a 1, what will the state be?
1, 1.
1, 1. Okay, perfect. You're on a roll. And if I send in 0 plus 1, what will the state be with my nice copier? If it were copying correctly.
0 plus 1, 0 plus 1.
Okay, so that's what a copier would do, but now what actually happens, so quantum mechanics is a linear theory, so what actually happens is I should write this as 0 plus 1 on my copy bit, and then I get to go to each of these things, so what this actually becomes is 0, 0 copy plus 1, 1 copy. Okay, so what my copier actually does is it entangles the photon to my copy bit. So it does not make a copy. This state is different than this one because this state does not have, this has cross terms. This has terms that look like 0, 1, and 1, 0, whereas this doesn't have any cross terms. Okay, so that is the my favorite proof of anything because it's like super easy to write down. And that's the generic example of why you can't do cloning. In any given physical system, there may be different mechanisms that cause that to be true. So, for example, if you have a system that has an amplifier, because you might think, well, that's how I'm going to clone something. I'll send my optical signal through an amplifier. The thing that prevents it from working is the fact that any amplifier has to have noise associated with it. So the amplifier, you think about exciting an atom, there's always spontaneous emission noise in an amplifier, and that noise exactly is enough to screw up the amplification process. Okay, so the eavesdropper can't clone the photon. If she could, of course, then she would clone it, she would hold it, she would send the original on to Bob, she would wait to hear the classical information about what basis she should use, and then she would always use the right basis to measure it. Okay, but she can't do that. And as we've just said, she'll introduce errors. They can detect those errors. And then if the bit rate is too high, they just discard the key. So again, what they're listening in on, the goal of this is distributing a random string of zeros and ones. If there is an eavesdropper, okay, my key is not secure. An eavesdropper might know part of the key. I just won't ever use the key. So I'm never actually compromising any real data with the protocol. And if the key is low enough, then they can do these protocols of error correction, which you saw a little bit in your homework, one example of, and then also so-called privacy amplification. So in privacy amplification, if you know how much information, if you can bound how much information an eavesdropper might have, they know 2% of your data or something like that, then you can reduce the overall size of your data in a way that makes it exponentially unlikely that the eavesdropper knows anything in the final string. So that's this classical technique of privacy amplification. So, the whole protocol has a lot of steps to it in terms of random numbers to figure out what sequence to send. There's doing the actual coding and quantum transmissions to Bob. And then there's a whole bunch of other stuff like synchronization, the classical discussion to do the sifting, reconciliation to find the errors, some quantum physics here to put a bound on how much information an eavesdropper could know, and then a whole bunch of other classical things like the privacy amplification, authentication. So that's going to be a key step. You have to know that you're talking to the person you're talking to. So this is one thing that's not always appreciated. If you have two people who have never met each other before and they don't share any information, you cannot do secure communication. You can't do secure quantum cryptography because an eavesdropper could always be pretending to be Bob, talking in a deep voice, and Alice doesn't necessarily know whether he's talking to Alice or Bob, and then the eavesdropper just plays along and pretends to be Bob the whole time, and you have no way of knowing. So there has to be some initial key information, initial secret information that Alice and Bob know. But once they have that, then they can start off the protocol, they can exchange key material, and generally what they'll do, they won't use all of their key material, they'll save some of it for the next session. And for that next session, they save 100 of their key bits, and they use that as the identification. Basically, the next time they talk to each other, Alice says, "Okay, tell me the first 50 of your bits," and Bob does, and then Bob says, "No, Alice, tell me the second 50 of your bits," and she does, and assuming they agree, then they know that they're talking to each other. Talking to each other and not talking to someone else. I guess the point of this diagram is that actually there's a lot of non-quantum stuff happening.
Why is the authentication happening after the state distribution?
I mean, it could happen in different places. It's because up to this,
Isn't it
I
necessary?
probably would have put it at the beginning rather than wasting time doing all of this other stuff first.
I mean, how do you even trust them for sifting if you haven't already authenticated?
Well, you don't necessarily trust them, but at this stage, we still haven't used the key for anything. You're only going to use the key once you have done all the final steps. So this is to say, I'm only going to use the secret bits on real messages that I care about once I've authenticated them talking to the person. It doesn't matter where you do the authentication. I probably would have put it at the beginning. I didn't write the slides. These were from Los Alamos National Laboratory. They happened to put it later in the stage.
Okay.
But it certainly needs to come before you actually use the key. I think that's the bottom line. So quantum cryptography does have other things in it other than quantum key distribution. Other things like two parties trying to compute something as an example. But certainly quantum key distribution is the most common example of it. And really, we could think about this as quantum secret growing because of the fact that you have to start out with some secret information, and then by doing this protocol, you're able to get more and more secret information. So I have this other phrase down here that's sometimes used. So one of the benefits of quantum cryptography is that it is future secure. So what does that mean? If you do classical public key encryption today to send some message, whether it's that you're having Chinese food or whether it's your nuclear launch codes or something like that, and someone next week gets their quantum computer working and can then apply that to the message and can crack that code, then they know a week from now that you are getting Chinese, you don't care. They know a week from now what the nuclear launch codes are, you still probably care. There are a lot of things that you want to have secure, and there are certain things that you want to keep secret for many decades. Not always the things you're maybe the most proud of as a country or something like that, but in any event, there are secrets you want to keep for a long time. If you're using public key encryption, which can be cracked by some future technology, that's a danger. In this case, as long as the technology to attack the system does not exist today when I'm distributing the key, then everything is okay, with the extra assumption that the enclave that's holding that secret key material is also safe. So it is true that if I write these secret keys into a hard drive and someone figures out how to scan my hard drive and get the data off that hard drive, they could do that a week from now, and then they know what the key is, and if they do that without my knowing it, then of course it's not secure. Let me ask if there are questions before we delve more into the specifics of implementations. Going once, going twice. Okay. So, this is kind of another look at the thing, and this one you'll be happy because it's got the authentication at the top of the protocol. So Alice and Bob, they start out with some large number of random bits, and then they don't detect everything, so Bob loses some of the key because not all the photons made it to Bob. That's their raw key. They talk over the phone. throw away roughly half of the, if they're equally choosing between the two bases, throw away half of the data approximately to sift to find the cases where they use the same thing. Then they find, okay, well really there were some errors, so they have to find those errors and correct them. And then, because there were errors and because they assume that they're all due to an eavesdropper, then they have to get rid of more data because she might know some of the keys, so that's the privacy implication. And then they're doing some final step of authentication. Okay. So this is just showing the, depending on where your error is, how many bits you have to exchange in order to find and correct the errors, according to, let's say, best known protocols. And I guess the thing to say is that, let's say you have a 10% error, the amount of bits, and let's say you have a large, you're doing this over a large data stream. The 10% error, you might naively think, okay, well I have to exchange 10% of my bits in order to find and correct that error, but that's certainly not the case. You have to exchange effectively almost half of your bits in order to find those errors, right? So that's, the moral of the story is you want to keep the bit error rate low in order for the thing to be efficient. Okay, I'm going to come back to the next two slides next time, so we're not going to do that right now, and talk about how we can actually use the key materials. So in some sense, the ideal would be to use it in a one-time pad where you're using one bit of the key per bit of the message. The problem is that a lot of our messages these days are pretty big, right? If someone sends you a nice photo or a nice movie, a video or something, that could easily be, hundreds of megabytes or gigabytes or something like that. And the keys, as we'll see, the key rates that people are talking about, I think the maximum that maybe people have maybe is about 20 megahertz or something like that. 20, I should say 20 megabits per second. Megahertz would say that it's coming exactly regularly. So 20 megabits per second. So, if you're trying to encode something that is 20 gigabytes, then you need 1,000 seconds in order to have enough key, and maybe the whole thing is not operating in 1,000 seconds. So probably this is not what would be used in most cases. Probably you would use that key, and that key would go in as a seed into some other random number generation algorithm that would generate something which is not exactly provably secure because it's based on a seed. So if someone knew what the seed is and they go into the same device, then they'll get out the same long string. But assuming that they don't know the other components that's inside the crypto logic, and they don't, or even if they do, but they don't know the entire key, then you'll get something that's completely random at the output, but something that's a lot bigger than what you started with. So you could then use that, for example, I started off with this public key encryption where you're going to distribute to everyone this large number, this large product of two primes. That doesn't get distributed very often. You distribute it and then you keep reusing it. You reuse that algorithm a long time. In this case, you could just keep resending this seed every second or something. Every second you could send another 100-bit seed that would go into the random number generator and give you a much longer random number string that you would use only for the next second. Okay, someone gets a quantum computer and they can crack that, but cracking, figuring out what that might be might take them a week, and they have to do it a week for every single second of data. It's not such a bad trade-off. So this is a photo of the very first quantum cryptography system that was ever built. It was working with a light-emitting diode as the light source, attenuated to the single photon level, and they had a Pockle cell that was used to rotate the polarization pretty quickly. The quantum channel was a whopping 13 inches or something like that. And then the receiver also had a Pockle cell to control what basis they're measuring in. And then going off to 2 photomultiplier tubes. Okay, so yes, 32 centimeters free space transmission. And Gilles Broussard had this nice comment that it was unconditionally secure as long as Eve is deaf, because in this case, whenever you fired the Pockle cell, they made a loud cracking noise because you're applying 3,000 volts onto the thing. And so if an eavesdropper heard the clacking noise, they know that the thing is operating in one basis and not the other basis. So that was, meant to be a funny comment, and it is, but it does highlight a problem that one has to be aware of. We always make an assumption when we're doing the whole quantum key distribution that the only thing, extra assumption, unstated assumption, it would be unstated except I'm stating it. So aside from the classical processing, the communication that we're going to do synchronization and reconciliation and things like that, and error correction, aside from those classical signals,